In this video, we'll look at some examples of calorimetry problems. We'll look at two types. We'll look at heat of reaction, which is the delta H associated with the chemical reaction, and we'll look at heat of solution, which is the delta H associated with a dissolving process. In this first example, we're looking at a reaction between copper sulfate as a solution, 50 milliliters of a 0.3 molar solution, and it's being reacted with sodium hydroxide solution. We've got 50 milliliters of each of these. And the concentration of the copper sulfate is 0.3 molar. The concentration of the sodium hydroxide is 0.6 molar. This is a double displacement reaction, so we'll produce copper to hydroxide. The charge is indicated here. The sulfate is -2. The second product is going to be sodium sulfate, Na2SO4. In deciding which one of these is going to be a precipitate, we can look at the simple solubility rules that tell us that the alkali metals will be in compounds that are always soluble, and so this leaves this to be a precipitate. When we balance this equation, we end up with 2 NaOH. Our goal here is to add to this balanced chemical equation a delta H value that will make it a thermochemical equation, which is what the question is asking for. So we need to determine the heat of reaction, or the delta H associated with this process. So in the experiment, what they did was they took the copper sulfate at 21.4 degrees Celsius in the calorimeter, and you want to assume that the sodium hydroxide was allowed to reach the same temperature to begin with. Then when we combine them, the temperature change is 3.2 degrees Celsius as it goes from 21.4 to 24.6 degrees Celsius. So that was the final highest measured temperature when you combine these two substances. Now, a couple of things. When we look at these values here, it's going to be important for us to be able to decide which one is the limiting reactant. And because they're in a 1-to-2 ratio and in the same volume, we can see that the concentration being double for the sodium hydroxide is indicating to us that there is no limiting reactant here. They are in stoichiometrically equal amounts. They'll run out at the same time. What you will see when we do our calculation is that we're going to choose to do our calculation in terms of copper sulfate. And the reason we're going to choose copper sulfate is because there's a coefficient of 1. Okay? It saves me a bit of time and effort with my delta H calculation. I'm not going to need to make sure that it's consistent with the stoichiometry because it's already going to be per 1 mole of copper sulfate when I do my calculation. We'll talk about that a bit more as we go through the problem. In this kind of a problem, we're assuming that the density of the solutions is 1 gram per milliliter, so the same as water, which is fine because the concentrations are low. And we're also assuming that the specific heat capacity of the solutions is the same as that of water. Okay, so that means that it will behave or absorb energy in the same way that water does. So to solve a calorimetry problem, there are 4 steps. The first step is to actually figure out how much energy is associated with the process. Now, if we think about this for one more moment, when you see this temperature increase, okay, we know automatically that this is an exothermic reaction. So the reaction itself is releasing energy to the surroundings and it's being absorbed. And so we're going to expect ultimately that our delta H is going to have a negative value. Okay, so it's good to have that kind of in mind so we can be checking our work as we go through the calculation. our first step is to measure the amount of energy that's associated with the process by determining how much energy is absorbed or lost by the solution in the calorimeter. So we're measuring the temperature of the solution. So MC delta T. The total amount of solution that we have is what we're going to use for the mass, the total quantity of mass in our calorimeter, and that's going to be 100 grams because we've got 50 milliliters of each and the density is 1 gram per milliliter. The C is 4.18. We've already been told that we are assuming the same as for water. And the temperature change, so T2 minus T1, is 3.2. I'm including units here so that you can easily see the unit simplification. You can see that our Q is going to be in joules, and the value here is 1337.6. So I won't round until the end. So this is the amount of energy that was absorbed so that we could experience the temperature change that we experience. That energy came from the reaction. So the reaction or the process that occurred released this amount of energy. So the sign is going to change in this step. So this is the amount of energy absorbed by the solution because this is the amount of energy that was lost by the reaction. Remembering that the energy lost is equal to the energy gained. Now this value here is the amount of energy associated for the particular process that we looked at. So for this exact example with these quantities. But when we want to have a delta H, we want that to be in general for this reaction. So that's why we're going to put it per mole. So this is per this many moles of copper sulfate, but we want to put it per 1 mole of copper sulfate. So in this step here, we're going to look at the Q of the reaction, and we're going to divide it by the moles of our limiting reactant. And so our moles of our limiting reactant is calculated by N is equal to C times V. We're dealing with a solution, so it's N is equal to C times V, and our volume needs to be in liters. So we have 0.015. So our negative 1337 divided by 0.015 moles, and that's going to equal 89.2 kilojoules per mole. So what I did here was I took the negative 1337.6 and I divided it, and then I divided it by 1,000. It's not very clear there, but there is a negative. So this is negative 89.2 kilojoules. So that's an exothermic process. And the last step is to make sure that it's consistent with the stoichiometry. And in this case, it will be because we forced it to be. So when we chose to put the moles in terms of the copper sulfate, that then made it so that we had 89.2 kilojoules per 1 mole of copper sulfate, which is what we want for this balanced chemical equation. Next, we'll look at heat of solution, and heat of solution is the heat associated with a dissolving of a substance, in this case into water. In most cases, we'll be looking at it in water. So in this example here, this visual, we've got sodium chloride dissolving into water. And what's important to recognize is that dissolving actually has multiple steps, and each step has a different energy associated with it. So ultimately what we're going to have when we dissolve something like sodium chloride into water, we know that we'll have the ions dissociated or broken apart within the water, and the water molecules will be surrounding it. So there's 2 steps that need to occur. The sodium chloride ions need to be separated. So, and separating those is requiring we need to overcome what's called the lattice energy. So you can see in this step, it requires 788 kilojoules per mole to break those apart into their ions. The heat of hydration, so when the water molecules are attracted to the positive and negative ions in sodium chloride, that's an exothermic process. It releases energy, and in this case it releases 784 kilojoules as indicated by the sign. So you can see the heat of solution overall to go from sodium chloride as a solid to it being dissolved is 4 kilojoules per mole. The net, so we required 788, we released 784, so the net requirement of energy was 4 kilojoules per mole. In this table here, we can see some different examples of different salts being dissolved into water and the heats of solution associated with them. What's interesting about this is to note that sometimes it's exothermic, sometimes it's endothermic for the dissolving process. It really depends on the relative quantities for those two processes, whether it requires more energy to break apart the ions or whether we release more energy when we attract the water molecules to those ions. And we'll, as we kind of investigate and study compounds a little bit more, we'll come back to this idea and analyze some of the theory associated with it. In this example, what we're going to be doing is looking at the dissolving of potassium chloride. Now, before we begin, what we'll do is look at what the process is that we're actually studying. So this is a physical change, and we are taking our KCl. I'm actually just going to cross this out. We're taking our KCl as a solid, and we are dissolving it in water to produce KCl aqueous. So one of the biggest mistakes that students make is they'll try to add water, H2O, and then try to write some kind of balanced chemical equation. But what you want to remember is that the dissolving process is simply going from a solid to aqueous. So we don't need to actually add H2O and have it in our balanced chemical equation. We are looking for the thermochemical equation, so we're wanting to determine the delta H for this process. So in the data here, we have the water, which is in our calorimeter, and then we're adding the KCl to it. So the water, we have 155 grams of it. The KCl, we have 5.4 grams of it. Its molar mass is 74.55. We'll need that later. The temperature of the waters, it starts at 22.8. and it drops to 20.9. So this is an opposite process. So in this process, we're decreasing in temperature. So this is an endothermic process. And so we expect ultimately our delta H will be positive. Okay? Our temperature change here is 1.9. So it's negative 1.9 because when we look at T2 minus T1, so 20.9 minus 22.8, we get minus 1.9 degrees Celsius. Now the other thing to kind of look ahead at is what are we going to be putting this in terms of? So in that step 3, when we do kilojoules per mole, what will we be using? It's going to be kilojoules per mole of the KCl, because that's what's in our process. So step 1 is to look at the Q of the water. So the water itself, what did its temperature do? It dropped. So we want to know how much energy the water lost as it decreased in temperature. Okay, and this is water solution, which is a little bit confusing in terms of the terminology, but it's the solution that's in the calorimeter. What's the energy change that it experienced? So MC delta T. Our mass is our total mass of the contents of the calorimeter. So we have 155 plus 5.4, so it's 160.4 grams. Same as before, we've got the specific heat capacity of water, and our temperature change is minus 1.9 degrees Celsius. You can see we've got unit cancellation here, and we're going to have negative 1273.9 joules. So this negative here means that the water, the solution, lost energy. That energy was lost to the system. So the system, or the dissolving process, required this amount of energy. So the Q of the reaction, and I'm putting reaction in quotes because this is actually a physical change, but when I say reaction here, I'm talking about the process that I'm studying. So the process that I'm studying, what did it do? It absorbed that amount of energy, 1273.9 joules. The last step is to put it in general. So in general, the delta H is the Q of the reaction, so 1273.9 per mole of the limiting reactant. So our limiting reactant, what's the only reactant, is our KCl. Our moles here is going to be calculating using mass over molar mass. So it's really important to kind of keep that clear. If I've got a solution, I'm using concentration and volume. If I've got a pure solid, I'm using the mass and the molar mass. So the moles that I have here are 0.07243. And I'm left with 17.6, and I usually just put the positive just to keep it clear. So this delta H, 17.6, and we've only got two significant digits, so when I attach it here, I'm going to round it to 18 kilojoules. Okay, we can write 18 kilojoules, or we can write 18 kilojoules per mole. In this last example, I'll leave it for you to do. We'll just write out the process to practice that and discuss a few things about it. But we're looking at the heat of solution of calcium chloride. So when you hear heat of solution, you want to think, okay, heat of reaction is for a chemical change. Heat of solution is for this physical change of preparing a solution. So we're taking our calcium chloride as a solid, and we are producing calcium chloride aqueous. Okay? And I want to know the delta H associated with this process. Okay? So in this case, we've got our initial temperature is 21.7, and this time we have an increase in temperature. So we're expecting this to be negative because this is an exothermic process. So the water that I'm measuring the temperature of, or the solution I'm measuring the temperature of, that temperature increased because the process that happened, the dissolving process, released energy to that solution that I'm monitoring. Okay? So you're going to go through the same steps. You do Q is equal to MC delta T to determine the amount of energy associated with the process. You flip the sign, and then you put it per mole. Okay? And you'll see the answer is there. You should get negative 81.7.